Good afternoon, dear professor and dear participants of the Climate Science Agriculture for Asia 18th TSAE International Conference. In this presentation, I am going to talk about thermal performance analysis of twisted tube absorber in a parabolic through collector under the variable flow condition. Let's turn to the introduction. The thermal performances of solar PTC is significantly influenced by design of the absorber tube, as it governs the efficiency of the solar to thermal energy conversion. Traditional PTC typically employs smooth circular absorber tube with a selective surface coating and vacuum insulation to reduce the heat losses. However, the thermal boundary layer developed in smooth absorber often limits convective heat transfer, especially at lower Reynolds number. To overcome these limitations, various passive enhancement techniques have explored, including use of twisted absorber tube geometry, which induces secondary flow and increases the turbulence within the heat transfer fluid. The twisted absorber offers a promising approach to enhance the thermal performance without the need for additional mechanical components or internal power sources. The introduction of the geometric modification in the flow paths, such as twists or helical structures, leads to flow destabilization, promotes mixing in the boundary layer, and increases the convective heat transfer coefficients. Such geometry can be particularly effective under the laminar and transitional flow regime, where natural flow development is otherwise limited. Moreover, twisted absorber tube have shown potential in improving the thermal performance while maintaining relatively low pressure drops, making them suitable for large-scale PTC integration. Material method. The physical parameters of analyzed absorber tube of PTC collector is demonstrated in the figure 1. Thermophysical properties of the receiver tube material is given in the table 2. The geometric view of the receiver tube of twisted receiver tube of solar PTC is given in that figure. In our study, employs a three-dimensional computational fluid dynamics CFD model developed in Comsol multiphysics to analyze the thermal performance of the twisted absorber integrated into the solar parabolic through collector. This simulation focused on evaluating the temperature distribution, velocity profile, and thermal efficiency under the varying inlet velocity. The results are compared against those conventional absorber tubes with the absorber tube to assess enhancement due to the geometric modification. And we have used finite element method for modeling, and in this page of the presentation you can see the result of and discussion. And we have simulated the twisted absorber tube at 4 different mass flow rate with 4 different material: stainless steel, iron, copper, and aluminum. As you can see, the surface temperature variation is relatively higher at stainless steel receiver tubes however, the copper receiver tube showed the lower temperature variation, lower surface temperature variation, because the copper has a better thermal conductivity comparing to the other material. That's why the copper is transferring the more heat to the heat transfer fluid. I mean that heat transfer fluid in copper receiver tube is relatively higher compared to the other material. In the next page of the presentation, you can see the inlet and outlet temperature variation of the receiver tube at 4 different mass flow rate. As you can see, you can see also here surface temperature variation of the receiver tube at 4 different velocity with 4 different material respectively. And you can see that the maximum temperature variation is observed with the steel receiver tube, and the next one is the iron and aluminum and copper. As you can see, the minimum surface temperature variation is demonstrated with the copper receiver tubes, because the copper, as I have mentioned, transferring more heat to the heat transfer fluid, which showing the better performance compared to the other material. That's why in our study we are suggesting to use of the copper receiver tubes with for the solar PTC as a good material, and twisted absorber tube can also enhance the thermal performance of the solar PTC compared to the simple smooth receiver tubes. Conclusion. In our study, a detailed safety analysis was conducted to evaluate thermal performance of the twisted absorber tube in a parabolic screw collector under the varying inlet velocity and material condition. The result demonstrated that stainless steel and iron with lower thermal conductivity result in higher heat transfer, higher surface temperature variation, but also cause a less uniform surface temperature. Copper and aluminum, due to the superior conductivity, show lower surface temperature variation, but showed higher outlet temperature, surface outlet heat transfer fluid temperature. As the inlet velocity increased, convective heat transfer improved, leading to lower absorber surface temperature and more efficient thermal boundary layer development, despite a modest reduction in fluid out temperature. Overall, the study confirms that material conductivity and flow velocity are crucial factors in the thermal optimization of twisted tube solar absorbers. The combination of copper and aluminum tubes with controlled flow velocity present a promising strategy for enhancing system reliability and energy efficiency. And thanks for your attention.